Yeah.
Yeah. Okay. Thank you very much. Great. Okay. So thank you very much, Professor Sahu, for the very kind invitation to give a talk in this Cosmos seminar series. So I'll be speaking about a specific theory that goes beyond Einstein's general relativity, which is the hybrid metric-Palatini gravitational theory. Okay, let me just say that this theory was also pioneered with a person that's also present in the audience, which is well, Professor Tiberi Harker. Okay, whoops, sorry about that. Just let me know if things are not working. I cannot see you, but okay. So here's the brief outline for the talk. So essentially, I'll be speaking about if there's a need for new gravitational physics. Okay, and when one speaks about new gravitational physics, one also speaks about the specific foundations of gravitation. What are the fundamental fields, you know? And one really goes down into the fundamentals to try to modify adequately Einstein's theory, okay? So when you, of course, Einstein's theory is the gravitational theory, okay? So anything that goes beyond GR modifies the gravitational theory, which is a standard one, right? So, well, we call this modifying gravity, modified theories of gravity. And of course, one of the most immediate extensions is F of R gravity. So I'll also just give a very brief outline of F of R gravity, just to, for the context and also some applications. But I'll be mainly speaking about the hybrid metric-Palatini gravity, okay? So, well, there's many gravitational theories. So the more pedagogical outline of this talk is if you modify GR in any way, you have to have some guidelines, okay, to see exactly what you're doing, you know, and then also the applications. So first of all, if you modify gravity, if you modify GR, you have to do the applications. First, you see locally if it passes the local tests, okay? Going into the weak field theory to see exactly if it's consistent with the observations, and GR has been very successful in this sense. So any modification of GR must pass these local tests, and of course it also has to explain the large scale structure of the universe and also the dynamics. And so the basic guidelines for modifying gravity with the applications is to see if all these theories that one comes up with must pass these tests. Okay, so that's really fundamental. So of course we know that the late time cosmic acceleration has forced theorists and also experimentalists, well, to pose a question. Of course, is GR the correct relativistic theory of gravitation? And the fact that GR is facing so many challenges, you know, such as the difficulty in explaining specific observations like the late-time cosmic acceleration, also the incompatibility with other well-established theories like quantum mechanics, and also the lack of uniqueness, because there are also other theories, well, in fact, many theories that explain the same thing in a much more, of course, complicated way than GR. So, is this indicative of a need for new gravitational physics? Okay, this is the big question that anybody working in modified gravity has to come up with. Okay, of course, well, cosmology is also an ideal test for GR. Um, um, more specifically, the late time cosmic acceleration, of course, you know. So a promising approach is to assume that at large scales, GR breaks down, and a more general action describes the gravitational field. And there's many hundreds, even thousands of theories that nowadays, you know, that do this. So if you generalize the Einstein-Hilbert Lagrangian, which gives you the Einstein-Hilbert equation, there's many ways to do it. Okay, if you're thinking about strong fields in the early universe, then you can try to explore R squared, where R is a curvature for strong fields. That term added to the Einstein-Hilbert term, R plus R squared. This R term squared dominates. there's also many other ways. One can also construct specific invariants, with specific quantities, like the contraction of the Ricci, the Riemann, the Weyl, etc. So there's many ways to do this. Okay. And of course, also the other specific motivations for these modifications of gravity is, of course, the possibility of a more realistic representation of the gravitational field near curvature singularities. There's been a lot of work done on this back in the 50s and the 60s, where people were also modifying gravity, but taking into account this motivation, and also to create some first-order approximation for the quantum theory of gravitational fields. Okay. So a very elegant way to go about modifying these theories is through the Lagrangian formalism. Okay, of course, GR is a classical theory, so no reference to an action is required. But taking into account the Hilbert-Einstein action, where R is the curvature, where you have matter is minimally coupled to the curvature, of course. But this Lagrangian formalism is extremely elegant and has its merits. Okay, so at the quantum level, the action acquires a physical meaning, and a more fundamental theory of gravity will provide an effective gravitational field at some specific suitable limit. Okay, very important. It's also easier to compare alternative gravitational theories through the actions rather than by the field equations. People working with modified gravity know that the field equations are extremely messy, so you can't get much insight by just playing around with the dynamics and adding terms to the field equations. It must be motivated by some Lagrangian formalism. And of course, in many cases, one has a much better grasp of the physics as described through the action instead of the field equations. Well, for instance, the couplings, the kinetic terms, and also the dynamical terms, etc. So let's move on to a very simple modification of the Einstein-Hilbert action. So there's no need to consider that the Einstein-Hilbert action is linear in the curvature scalar. So one can also consider that it's a function of R. Okay. And this is also very appealing because it combines specific mathematical simplicity and a fair amount of generality. But in this case, we verified, taking into account the trace equation of the field equations, that the Ricci scalar renders a dynamical degree of freedom. Okay, so it propagates, and this introduces a new light scalar degree of freedom. This is really important because it does reproduce the late-time cosmic acceleration, which is very good. That's what we want also. But also this light scalar strongly violates the solar system constraints. Okay, and the way out is through this so-called chameleon mechanism. Okay, so the scalar field becomes very massive in the high-density backgrounds, and one can assume that f of r gravity is viable in a sense. Okay, I think people working in these theories back in 2007, 2008 will remember exactly what was going on. People were trying to discover exactly what was wrong with f of r gravity with this light scalar field. For instance, people working with the weak field, there was a paper coming out which proved that the ppn gamma perimeter was equal to to 1/2. So they ruled out f of r gravity. And then the following week, there was another paper by people with big names, right, who proved that the gamma was equal to 1. And it was many months that things went on this way. So it was very exciting and very intriguing doing research in f of r gravity back then. And then, of course, finally, people figured that one can viabilize f of r gravity through the so-called chameleon mechanism. Okay. Anyway, so there's specific approaches to modify gravity. In particular, f of r gravity, one can take into account the metric formalism, where the fundamental field is the metric. So it's a metric that mediates the gravitational interaction. One can also take into account another field, which is the connection. So now one sees that there's quite a confusing nomenclature in the literature, where there's the Palatini formalism, there's a metric-affine formalism. But the Palatini formalism specifically tells you that the f of r is also a function of the connection. So there's two fundamental fields. There's a metric and there's the a new connection. Okay, the metal-Lagrangian in the so-called Palatini formalism is not coupled to the connection, only to the metric. The metric-affine formalism in this nomenclature is when the metal-Lagrangian is also a function, is also coupled to the connection. So there's these different approaches. Okay, a lot of work has been done on this, and we know exactly what's going on here. Of course, one can go back to a scalar tensor representation where the metric formalism is equivalent to a Bronsted-Sticky formalism when the Bronsted-Sticky perimeter is equal to 0. Okay, so that gives you a specific Bronsted-Sticky Lagrangian. In the so-called Palatini formalism, if you go to the scalar tensor representation, that's equivalent when the Bronsted-Sticky perimeter is equal to -3/2. Okay, so this tells you exactly that both approaches in f-of-r gravity are two completely different theories. Okay, because they give you different dynamics. All right. But one can also try to unite both formalisms, okay? Because both formalisms, the metric and the Palatini, also have some drawbacks, okay? Well, we know exactly now what's going on, you know. Well, the metric formalism gives you fourth order coupled differential equations, which one has to be very careful of this because of the instabilities, there's ghosts, and there's in fact, one knows exactly what to control now at this moment. The Palatini formalism also has some drawbacks, also depending on one's point of view. So this motivated several researchers back in 2011, 2012, you know, to try to unite both of these formalisms, and it was very exciting what was uncovered. Okay, so in fact, the Palatini, the hybrid metric Palatini theory, takes into account both approaches. So for simplicity, we consider the first term in equation. I think that you can see my cursor, right? So the first term in the action 3 is the R, is the metric scalar curvature. Sorry about that. And we just which gives you GR, of course, and we just kind of perturb it around some specific f of R. Now, this new R is built in terms of a new connection, okay, which is given by this this relationship further down, okay, which I've just highlighted. So in fact, this curly R is a new specific degree of freedom, okay, because it's a new curvature that's constructed in terms of a new connection, okay. So there's been a lot of reviews on this, and I'll put some references there for your information. Okay, so if you take into account now the action given by equation 3, and you vary the action with respect to the metric, okay, it gives you equation 4, which is the gravitational field equation. Of course, taking into account the standard energy momentum tensor definition, which is given by equation 5. But now when you vary the action with respect to this new connection, it gives you the equation of motion for the connection, and one sees that this new connection is the Levi-Civita connection of a new auxiliary metric, okay, which is given by this h mean u, okay, which is given in terms of the f, which is the scalar field. I mean, if you go into the scalar tensor representation, but it's a function of the what one can call the so-called physical metric, okay, which is the g mean u, which is what is coupled to the metal-Lagrangian. Okay, so this new auxiliary metric is conformally related to the physical metric through this conformal factor, like I mentioned. Okay, and of course, one can also write this as a scalar tensor theory, which is much simpler to work with. Of course, one can work in this geometric curvature representation, but it's quite messy. So it's always easier to work in the scalar tensor representation of the modified theory of gravity, which is taken into account. Now, for people working in f-of-r gravity, you'll see that there's a perimeter, the omega, which is -3/2, which is it's the Bronsted-Sticky perimeter. And if you alert, you'll see that that's exactly what the Palatini formalism gives you, like I mentioned just now. But there's a big difference here with the hybrid theory because the curvature is coupled to 1 plus phi, okay, which is different to the coupling in the specific Palatini formalism. And this is very simple, but it has a lot of well, physical consequences, okay? So, well, to give you a feeling of this, so if you vary the action with the action 7 on this scale tensor representation with respect to the metric, you get the gravitational field equation given by equation 8. So, of course, here you also see that the space-time curvature, okay, given on the left-hand side, is also generated by both the matter and the scalar field, okay? If you prefer to work in the Einstein frame, then you can do a conformal transformation to go into the Einstein frame, taking into account the transformation given by equation 9, and this gives you the Einstein frame Lagrangian, which is given by equation 10. Okay, so this can be put into a canonical form by introducing a new rescaled field given by equation 11. And this is very neat. And if you prefer to work in this specific Einstein frame, you take into account these transformations, and sometimes it's much easier to work in this. Okay. Okay. Now, what is really important is the weak field slow motion behavior. Okay. So, like I mentioned at the beginning, if you conjure, if you will come up with a specific modified theory of gravity, you have to see if it passes the local tests. Okay. So that's what was done also at the beginning, and take into account, like I mentioned, the weak field and the slow motion behavior. I'll just give two specific perimeters, which is quite important. So the effective Newton constant, which is given by G effective by equation 12, and the post-Newtonian perimeter, the PBN gamma perimeter, which is given by equation 13. We know through the observational test that gamma must be equal to 1. Okay, that's exactly what we need also in F of R gravity. Okay, because that's what the observational tests give us. Okay. Now, what is clear from these equations is that the coupling of the scalar field to the local system depends on the amplitude of the background value for the scalar field, okay? So if the background value, if the phi 0 is very small, then one sees immediately that the GF, the effective Newton gravity, is equal to the G itself, and gamma is equal to 1. That is regardless of the value of the effective mass. So we have here specifically two mechanisms, to pass local tests, okay? If you impose, like I mentioned here, a background field, which is very small, you regain GR, okay, at the background level. Now, it's also very pedagogical to try to confront this with F of R, okay? So in F of R gravity, we have here the specific perimeters. We see that the GF, the effective Newtonian gravity, is given by equation 15, and the gamma is given by equation 16. So the gamma is equal to 1 only if the effective mass is large, okay? So this, it must be large to make the so-called Yukawa type corrections negligible in terms of the local experiments. So here, well, specifically, this is what is called the so-called Canadian mechanism, okay? When it's a large mass for the gamma to be equal to 1, okay? And it's very interesting that we don't need this in a hybrid theory, okay? So this is one big advantage relative to the F of R metric formalism in terms of the weak field. So what about the large-scale structure of the universe? Okay, so we also have to, like I mentioned at the beginning, we also have to see exactly what happens at the large scale, what happens in cosmology. Okay, so I'll just write a few equations for your information for people who work on this, so you can see exactly what's going on here. So people working with F of R gravity in the scalar tensor representation, one can see that equation 17 and 18 are very similar to the so-called Palatini formalism, okay? But there's a big difference here because there's a factor of 1 plus phi. And once again, that makes all the difference. One also verifies that you have a modified Klein-Gordon equation, which is the equation of motion for the scalar field, which is given by equation 19, also specific. So to give you a specific model, okay, to see exactly how one can construct pedagogical solutions, okay, let's just consider a quadratic potential for mathematical simplicity given by equation 20, okay? So the trace of the field equation automatically implies that relation that's just below equation 20. Due to cosmic expansion, the trace tends to 0, and this naturally evolves into a de Sitter phase, okay, where the V0 perimeter will be proportional to the cosmological constant. Okay, this also for consistency with observations. Now, if V1 is positive, then the Sitter regime also represents the minimum of the potential. And if you take into account that the effective mass for local experiments is given by that equation, and it's positive for when phi is less than V0 over V1, that must also be obeyed. But when V1 is much larger than V0, the amplitude is small enough also to pass these solar system tests, okay? So this is also very interesting because the exact de Sitter solution is compatible with the dynamics of this scalar field in this model. So the parameters pass both local tests and large-scale tests in a specific model. If you want now to do much more cosmology, for instance, in the cosmological perturbations, I'll give you a specific recipe, what you can do. So to understand the cosmological structure formation, we need to deduce the perturbation equations and analyze them for specific cases, of course. So this paves the way for a detailed comparison of the predictions with the cosmological data on large-scale structure and the CMB, for instance. If you consider the specific Newtonian gauge, which can be parameterized by two gravitational potentials, which are given by equation 21, and if you consider that the matter source is a perfect fluid with a background equation of state omega, or W, and we have a specific density perturbation and also a pressure perturbation with velocity V, we verify that the two gravitational potentials are related by equation 22, which are proportional to the scalar field in the hybrid theory and its derivative, and then the perturbation. So assuming a perfect fluid, we have two very important equations, which are the continuity and the Euler equations for the matter components, which are given by equation 23, 24. I've just presented these two equations for your information to see exactly what's going on. For people working with cosmology, you can see exactly what differences there are to models that you work on. And also the linear part for the Klein-Gordon equation is quite complicated. After tedious calculations, it gives you equation 25. Okay. So what about the matter-dominated cosmology? So if we consider that the formation of structure in a matter-dominated universe, where the omega is equal to 0, this assumes, of course, scales deep inside the Hubble radius. It's a so-called quasi-static approximation. And also combining both the continuity and the Euler equations given in my previous slide, this gives you the growth of structure given by equation 26, where the effective Newton gravity constant is given by equation 27. So if you take into account the background, where the background scalar field is very small, it gives you specifically the Newtonian constant. Okay, so it's like I mentioned, equation 26 provides a very simple approximation to track the growth of structure accurately within the linear regime during the matter-dominated cosmology. Okay, now this has also, of course, has to be confronted with specific observations, and one can do this, of course. Quite a lot of work has already been done here in this, but also it's to give you exactly what a kind of a recipe or guideline, what can be done within this specific hybrid metric-Palatini gravity. And also the vacuum fluctuations. So the propagation of the scalar field of freedom in vacuum is also extremely crucial to check the consistency of the theory. Okay, so if you consider vacuum, of course, the curvature perturbation in the uniform gauge field is given by that equation given by equation 28, sorry, the zeta, in terms of the Newtonian gauge perturbations. And the evolution equation is given by equation 29, which is extremely messy. But this gives you a general equation to study the fluctuations in the hybrid gravity inflation model, for instance. One can also go into the Einstein frame, which is usually quite simpler to work with. And so one can do a lot of work over here. Not much work has been done in the specific regime, so that's also an open question, but it seems promising. Well, the first approaches are quite promising. Okay, so let me just give you brief outline, okay, of what can be done. Of course, once one has this specific hybrid metric-Palatini theory under control, so now we have a new building block. Okay, so we have a new Levi-Civita connection, which is well related to a new auxiliary metric. Okay, so if you have this new building block, okay, one can construct different curvature invariants. Okay, so for instance, one can consider a plethora of these invariants. One can consider invariant quantities, both through the Palatini curvature quantities, like the contraction of the Ricci-Palatini curvature, or the metric, and also mixed quantities, the Riemann, etc. Okay, so there's a whole new building block, a whole new theories that can be built through specific invariants. Okay, or constructed through this new building block. So I mean, it's quite exhaustive to go through all these theories. So one also has to have a kind of a simple guideline to see exactly which are the theories that need to be or could be investigated. Okay, so I'll just give you also a pedagogical outline of how to do this with a specific pedagogical example. So if you consider the action given by equation 31, okay, we have f of r metric r curly, which is the Palatini, and a coupling, a mixed coupling between the Ricci tensors of both Palatini and metric quantities. Okay, so it's quite interesting to see exactly what this quite simple theory gives. Okay, it's not that simple because you have very messy equations. But for instance, when you vary the action with respect to the metric, it gives you that field equation, which is quite messy. The quantities you see the f of r curly, f of r q are defined in terms of the derivatives of f with respect to the respective quantities. Okay, I won't go much into the field equations, but or to give you a specific summary of what happens here. So if you vary the action with respect now, the action 31 with respect to the connection, you see that you have a new Levi-Civita connection, which is given to the auxiliary metric, which is the g hat, given by the first term in equation 32. The r mean u is given as a mixture of those two quantities in equation 32. So that's the new metric. Given in terms where you have the Levi-Civita, the new Levi-Civita connection given in terms of this auxiliary metric. Okay, quite messy in fact. But now let's see exactly what can be done here, and to see exactly which are the theories that are quite devoid of instabilities and pathologies. So take into account the graviton propagator. Okay, we consider perturbations around Minkowski space. Okay. And when you invert the linearized field equations for the physical metric, this does provide the propagators for the graviton and also the additional degrees of freedom that may be present in the linear perturbation. One verifies that the propagator is defined by equation 33, where the right-hand side represents the linearized stress energy source. Okay. So in the formalism, I won't go through this in detail, but just give you a kind of a summary. But in the formalism of the spin projector operators, the result can be given in Fourier space in terms of two functions, a and c, which I will define in the next slide. But the propagator is given by equation 34, okay? Where the P2, with that so-called P squared term, picks up the spin term, and the P0 is the scalar modes of the fluctuation. So these quantities here, a and a c, the small a and the small c, are given in terms of equation 36 and 37, just to give you an idea that these quantities are given in terms of the specific f that you're considering in your equation 31, okay? The big A and the big B are given by equation 35. So now if you consider specific examples, all you have to do is just apply this formalism to see exactly what your propagator will give you. For instance, if you will consider the specific f of r gravity model, okay, where of course the big A is equal to 0, one verifies that the graviton propagator is given by equation 38. So this picks up an extra scalar degree of freedom, and this was to be expected, okay? Because well, we know that the f of r models are known to be equivalent to a Brown-Sticky theory with a with a vanishing Brown-Sticky perimeter. And the mass of the scalaron, which is given by the second term in the denominator of equation 38, must be positive, okay? And of course, the f prime 2, the second derivative, must be positive for the theory well to be stable. This is exactly what we know from f of r gravity, okay? This is one of the conditions that must be imposed in f of r gravity for the theory well to be stable, and it also what comes up naturally from this graviton propagator or formalism, okay? So it must be stable, otherwise we have a tachyonic mass which spoils the stability around Minkowski space. So this is quite intuitive. So it's also to give you a kind of a specific intuition to see exactly what this graviton propagator or formalism gives you. And it does reproduce the specific results that we know from f of r gravity. What about f of r gravity in the Palatini formalism, okay? So we know that f of r gravity, like I mentioned before, is equivalent to a Brown-Sticky theory with the perimeter, with the Brown-Sticky perimeter equal to minus 3/2, okay? This specific value corresponds to a vanishing kinetic term of the field, which is thus non-dynamical. So this is very transparent when you take into account the modified Claude-Gordon equation, which with the box of the scalar field term appears multiplied by an omega plus 3/2 term. So take into account that the Brown-Sticky perimeter is equal to minus 3/2. That term is 0. So we have a non-dynamical degree of freedom, okay? So therefore, we expect that no additional scalar degree of freedom should appear. What does the graviton or propagator formalism gives you? So take into account the specific definitions, we verify equation 39. So of course, that the graviton propagator in f of r Palatini is precisely what one would expect in JR. And that's what we would also expect from our analysis. So what about, for instance, in hybrid metric-Palatini models in the specific one that I showed you, the R plus R f of r, okay? So in Ricci flat spacetimes, the hybrid metric-Palatini theories share the properties of the Palatini f of r theory, which in vacuum reduce to GR with a possible cosmological term. So knowing this, with hindsight, our intuition tells us exactly that, that the graviton propagator should also be identical to the GR, and take into account all the specific formalism that I showed you before. That's exactly what it gives. So it's not a surprise that we find no new propagating degrees of freedom in Minkowski vacuum. And so the linear model that I showed you at the beginning is extremely promising because it gives you also GR in the spectrum level, okay? So if you now take into account a much more complicated theory, for instance, where you have the R curly, the Palatini curvature and the Q term, one verifies that the graviton propagator is extremely messy. We have specific poles, and one can readily see that this theory is seriously haunted by ghosts, and thus can be considered to be non-physical, okay? One can also take into account more specific analysis, and one can see exactly which of the quantities that should produce stable solutions. And there's a paper that came out a couple of months ago take into account this, okay? So I didn't cite it yet, but you can have a look at the paper which came out in the early part of the year that takes into account this in much more detail. So it's quite easy to convince oneself that this occurs very generically. Okay, these instabilities. So once one starts building the actions from higher order curvature invariance. Okay, so the moral of the story is that simple linear R plus f of r curly is extremely promising. Okay, this also motivated us to do some much more work over the years, taking into account the dark matter problem. So we saw that the perimeters were compatible for the weak field limit and also for cosmology. But what about the intermediate model scale? Sorry, in galaxies. And quite a lot of work was also done here. And we also found that the perimeters that were imposed by the local tests were also compatible for explaining the effect rotation curves in the galaxies. That is, it mimics dark matter. So take into account these models. It's not really necessary to impose dark matter at this level. Okay, a lot of work was done. I mean, there's also much more recent work. I mean, in specific hybrid metric-Palatini stars, there's been a lot of work in the vacuum solutions, in cosmic strings, and also the wormhole solutions were also done here. A lot of work was also done with the generalized f of r gravity. The first R, of course, is the metric quantity. The second R is the curly one, is the Palatini one. So also a lot of work was done here in these models. Well, also taking into account the early universe, also the playtime cosmic acceleration, it was found compatible for these two regimes. And of course, also if you're interested, you can also have a look at this book, which I wrote with Tiberi Harko. It was published in the Cambridge University Press, so it's got all the formalism and all the applications here. It also takes into account the curvature matter couplings, which I didn't speak about. So I'll just summarize the talk. So we presented a hybrid metric framework for specific theories of gravity, and we tested these new theories and through specific the observational tests and found which were the perimeters that passed these specific tests. Very important is that these theories, these hybrid theories, evade altogether the so-called chameleon mechanism, which is very promising. Many people don't like the so-called chameleon mechanism because it's quite contrived. Okay, so if you don't like the chameleon mechanism, here's a theory which evades it altogether. It also excludes theories inhabited by ghosts like superluminal propagated and otherwise pathological degrees of freedom, like I showed you with the graviton propagator. So more generically, in terms of a specific monistic view of physics, one would expect nature to make somehow a choice between the two distinct possibilities offered by the metric and the Palatini formalisms. But in fact, here's a theory that's consistent with observations and combines elements of both of these approaches. So it seems like that the gravity admits a diffuse formulation where a mixture of both formalisms allow to successively address large classes of phenomena. Future outlook, of course, tests from the solar system, from large-scale structure and lensing are extremely important to constrain your models. We also know, of course, that modern surveys such as the Euclid and amongst others will provide new opportunities to test these different cosmological models. And of course, we also know that the wealth of this unprecedented high precision observational data will become available by these upcoming and planned surveys. In fact, we have already dawned in a golden age of cosmology. And of course, this does offer a window into understanding the nature of the late-time cosmic acceleration of dark matter and, of course, of gravity itself. So I hope that I did transmit to you a pedagogical approach to gravity. Okay, exactly what one needs to do when you have a specific modified theory of gravity. Take into account the weak field limits, the cosmology, and you test them. in fact, we're going through a crisis now at this moment because there's so many modified gravitational models, So which is the correct approach? So that's an open question which I will leave to you. So thank you for your time and for your attention.
So thank you, Professor Francisco. So it is a nice talk. So it is open for the discussion. So anybody have any queries? Yeah, please. Saintan, you can start.
Hello, sir. Can you hear me? Yeah.
Yes, I think so.
Okay. Yeah. So first of all, thank you very much for this talk. Also, thank you and Professor Harko for the book. It's really helped me. The Cambridge monograph. So I have basically two questions. The first question is basically when we are doing the Palatini gravity in normal GR, we actually vary with respect to connection. The equations are much more easier because delta of connection is a tensor. But in a sense, the connection is a dynamical variable. We use the Lagrange's undetermined multiplier to get the connection formula, right? That half G mu nu is the Cristobal symbol formula. So I'm just asking that when you are taking this hybrid one as like the connection as an independent dynamical variable, you are assuming that you are equating with respect to the like the Cristobal symbol later. I'm just asking that whether, how do, for a general, so FT or F2 gravity, like the torsion wave, how do one recover the connection formula? One uses still the Lagrange's undetermined multiplier to get the formula. So that's what I'm asking, that how does the general Palatini constraint, that is that when you are taking the variation with respect to gamma, how do one recovers the connection in terms of metric? One still uses the Lagrange's undetermined multiplier method? So that's what I'm asking.
Yes, I think that you answered the question. One can take into account the Lagrangian multipliers. I don't know if I really understood your question as how does one obtain the connection?
Yeah, in a sense that if I want to recover the connection formula in terms of metric, so I have varied with respect to the connection. Connection is my independent variable. And if I want to recover it, just like in the normal Palatini formulation, we derive the formula of connection using some Lagrange's undetermined multiplier, like, in a sense that's the constant. So I'm just asking that, is it very susceptible in a sense that can we always recover the connection from this? Because in FT or FQ, the connection has more degree of freedom, right? Because it is not symmetric, etc. So that's what I'm asking, that is the method is always...
So I showed you. Well, in fact, how do you? So I think that your question is how do you get the new connection, right? So if you vary your action, well, with respect to the connection, right, you get a propagating degree of freedom for the connection itself, okay, which is a function of the conformal factor and all that, okay. So one can reduce that to a specific equation of motion for a new auxiliary metric, okay, exactly how it stands for the derivative of each other, right? So one can redefine a new metric, okay, which I called the so-called auxiliary metric, okay, which was the H, right? And in terms of that H, one can define your new connection, okay? But that new H, that new auxiliary metric is given in terms of your physical metric plus the conformal factor, okay? So so your new connection is the Leverage one of that new auxiliary one. And if you know the exact form of that auxiliary metric in terms of the physical one can also reproduce the new connection in terms of the physical metric, okay? So I think that's what you're asking, right?
Yes. So in a sense
I'm
that
not sure.
so in the well part of the metric, like whatever the one, that would still hang around, right? The auxiliary part would still be there.
Yeah.
And
Okay,
just one small question. Okay, thanks. This is fine. I'm just having one small question. When you are splitting the metric in the conformal Newtonian gauge, that is 1 plus phi and 1 plus phi. So could you just go to that slide? You are probably using the growth vector.
So 1 plus phi, that's not the... well, let me have a look what you want to see.
The Newtonian gauge.
This one?
Yeah,
this one,
that's before that slide. While the
Not
metric
this one?
is split. Yeah, just before that,
With a
when the
metric.
metric is split. Yeah, that's
Yeah.
it. Yeah, I'm
Yeah.
asking that when the reason why we take this conformal Newtonian is because in the super Hubble horizon, this phi and psi gives us the Poisson equation, right? I mean, in a sense that we can do.
Yes. Yes.
So I'm asking that because we are doing a hybrid Palatini formulation, our metric would not be associated with this. In a sense that if we make a burden like gauge invariant potential, there would be some auxiliary capital omega would be hanging around, right? So is that a problem?
Yeah.
So that's what I was wondering. That even for metric
Yeah. Yeah.
Palatini,
No,
is this
that's
still
right.
okay?
That's right. So, right. So that also depends on how you define your gauge. So over here we take into account the body potentials. Okay. There's also other ways to do it. Okay. But here we take into account the body or potentials, which is much simpler, in fact.
But the
Okay.
gauge, I mean, it might not be gauge independent, right? Because your metric has an auxiliary term, like the capital omega which
Yeah.
you take. So is this still gauge invariant with respect to the auxiliary metric also?
Um, That's a
Okay,
good
maybe.
question. That's a good question. Yeah, but it's a good question. At this moment, I don't know how to answer that. I know that there's specific ways to do this gauge. Okay, if it's gauge invariant, I'm not sure now. Okay, I do suspect yes, it is, but I don't know exactly why, and I can't give you a specific answer now at this moment. But I can have a look at it, and then we can talk later, I think. Okay.
Sure, sure. Okay, thank you very
Sure.
much for this. Thank you.
Sure.
Yeah, anyone else? Yes. Yes, Professor Visham.
Hello, Francisco.
Hello.
Thank you very
Uh-huh.
much for a very nice talk. Can you just comment about the Hubble tension in this theory?
Yeah, that's a good question. I haven't worked on that specifically, but that's a good question also. So I do gather, well, we have now a specific extra degree of freedom. So one has some freedom to try to explain the Hubble tension. Okay, I'm not sure exactly. That's open work in the hybrid theory. Okay. But my gut feeling is that we'll take into account this new extra degree of freedom. One can fine tune it somehow, okay, to solve the tension itself. Okay, that's my first gut feeling. But that's an open question in hybrid theory. I'm not aware of any work that's been done yet.
Thank you.